we talked about volumes of solids with if we knew the cross section, and now we're going to talk about another way to find volumes of solids, and that is by basically revolving a region around a line, which may be the x or y axis or could be another line. And we're going to use that. And so this first method is going to be called the disk method. And so it's called the disk method because basically we make a bunch of little disks that have a small width, like little cylinders, like you see in the pictures here. So you have a rectangular strip. So you're going to draw a rectangle just like we've been drawing, which is why I said it was real important. And it's going to be revolved, though. If you look at this picture, you can see how it's revolved around the axis. So in this case, the x-axis. So your rectangle for the disk method will always be perpendicular to the axis you're revolving around. And so if we look at this, we can see, so the first question is, okay, what's the volume of this cylinder if the height of the rectangle is considered r and the width of the rectangle is dx? Well, if we look at this cylinder, you have to kind of think of this cylinder like it's laying on its side. So here's say the top of, like, this is kind of like a tuna can. There's the top of it. And so when we're talking about the radius of the cylinder, we're actually talking about this rectangle right here. That's going to be your radius, if you see that circle. And then your height of your cylinder is this direction. So that's like if you have a tuna can on its side, if you can think of it that way. So if we want to find the volume of the cylinder, then we're going to have, it's going to be the area of the base, which is pi r squared, because it's a circle, times the height. Well, in our picture, pi, of course, is a constant, but the radius, well, they just said let the radius, the height of the rectangle here, this height right here is going to be capital R. So that means our radius is capital R squared. And then the height of your rectangle, well, the height is this distance going this direction, or it's right here. That's actually the height of your cylinder, which is, of course, our delta x or dx, whichever way you want to look at it. And so this would be dx. So there's going to be the volume of that little cylinder. So that's the heart of the disk method. So here are your two different ways that we can have this happen. So we can have a horizontal axis of revolution, which means that the rectangle is going to go, the width will be along the x-axis, and so it will be in terms of x. And if you're going to have that, then that would be like, you could basically draw a little picture here. You're going to have your rectangles going this way that you're going to draw, your representative, and it's going to be going around the x-axis this way. And so your rectangle's width there is your dx. That tells me everything's with respect to x. Well, I might have some region that just goes from here to here. So I'm going to integrate from A to B, whatever that is. And whatever my region might be, this is the height of it, where my rectangle is. And so the radius of your cylinder, as you revolve it around, you got to imagine your cylinder coming around here. Okay, and then you have the back side. So here's your cylinder. That's one representative cylinder, and then there's be infinitely many of them. But the radius of that is simply going to be to go from the function itself up, or from the x-axis that we're revolving around up to the function. And so that's going to be your radius. And then it would be similar to go around the y-axis. So on the y-axis, though, you would have your rectangle going this way, and where you would have delta y for your width, and you would be revolving around the y-axis. And it would be the similar kind of thing. And so those are your heights of your little representative rectangles, and those are really important. That's why we talked about that for area, how important it was to start that. Okay, so let's look at this example. So we're going to draw a rectangular strip here so that we can find the volume. Now the picture on the bottom there is just what the surface would look like after it's been revolved around, just so you can kind of see what that looks like. So here we want to go to our picture and we want to draw a rectangular strip Well, we're going to be revolving around the x-axis, and I like to always draw my figure showing we're going around the x. And so my rectangle needs to be perpendicular to the x-axis. So I'm going to draw a rectangle here, and that's going to be my representative rectangle, which means the width is going to be dx or delta x. And now I should be able to easily write my expression here. So the volume of one cylinder, so this is just a representative cylinder that I have. The volume is going to be pi r squared again times dx. Well, in this case, r is this distance if I go all the way up and down this rectangle. And then remember, I have lots and lots and lots of these, and they're all going to get revolved around. Well, the height is always going to be from the x-axis up to the function. So this is going to be pi, and your capital R is just going to be 4 minus x squared, because that's the function, squared dx. So if I want to find the entire volume of this entire figure down here, then I've got to add up all those cylinders. That simply represents one of the cylinders, but we would have infinitely many of them. We would add them all up, and we would make the widths go to 0. Same idea as we did before. Now I always put pi out in front, and then it's dx, so we need to look on the x-axis, so that's 0 to 2. So we're going to integrate from 0 to 2, and then I've got my function here. So I have 4 minus x squared, whole thing squared, dx. So that's going to give me pi times the integral 0 to 2. I need to multiply that out, so that's 16 minus 8x squared plus x to the 4th dx, and then just continue with the integral. Once you have it set up, the rest of it's really easy. It's just using all the methods that we've done. So we're just going to integrate each of our parts, and then substitute our values. It's 0 to 2. So of course we plug in 2 first, so we get 32 minus 2 cubed is 8, so 64 over 3 plus 32 over 5 minus parentheses. Well, all of these have an x in them as in the top, so when you plug in 0, you're going to get 0 for everything. Now don't assume it's always 0, but it certainly is if I plug x in. Now you can do some more steps. I'm not going to do that here. We're just going to get to the answer, that the volume is 256 pi over 15. Be sure you practice that, especially if you're really bad at your fractions. Don't skip that, because on the AP test, the last thing you want is using your time up because you can't add 64 thirds and 32 fifths. Okay, so make sure you practice that and get your common denominators. Okay, so let's go on to another example. So here's another one. And this time it says we want to revolve this solid around the y-axis. And then on your page, you have the picture on your notes of what this will look like after you revolve it. So I want to always mark that I am revolving this about the y-axis. So I always mark that. This is the direction. So if I'm going to use the disk method, my rectangle must go this way, because it has to be perpendicular, because I'm going to make a bunch of cylinders that are going to spin around. So that makes my width dy, which means everything here is going to be in terms of y. Well, we have y equals square root of 16 minus x squared. Well, that's going to have to be changed to be x equals something, because everything has to have a y as in your function. So I need to square both sides, get x squared by itself, and then square root both sides, which would give me plus or minus the square root of 16 minus y squared, but we can see from the picture we're on the plus part of that. And so this is what x will equal here. So I've now got my function solved in terms of y, and so now I can set up my integral. So my volume is going to be it's going to be, it's basically, just think of the formula, it's pi r squared. So I have pi, and I integrate from somewhere to somewhere. Well, remember, my rectangle is dy, so that means I use y values. So this region goes from 0 to 4, and then I just need the radius squared. Well, the radius is simply this distance from here to the top of any particular rectangle. Well, that's always going to be the function value. And I just solved that, so that's going to be the square root of 16 minus y squared, whole thing squared, dy. So your formula is basically, again, pi r squared. And that's how we get the formula. So now if we just do our integration here, let's simplify first. So we're integrating pi times the integral 0 to 4. Well, you square root and then you square it, you're just going to get underneath. And then go ahead and do your integration. So we have 16y minus y cubed over 3. And we're going from 0 to 4. So you're going to have pi times 64 minus 64 thirds minus, again, you plug it in, you get 0 for both. So this will end up being 128 pi over 3. And that's going to be your answer for volume. All right, so now on this example, this is the last thing that we need to learn how to do, and that is revolving it around somewhere else. So this is not revolved around the x or the y axis. So this time we're going to take a region that we need to draw. So we're also going to have to draw this one, and we're not going to revolve it around the x or the y axis. We're going to revolve it around a different line. So first thing we need to do is draw this picture. So if you don't know what something looks like, then of course you always just plot points, plug numbers in. Well, let's write the things we do know. We certainly know how to graph y equals 2 and y equals 6. So here's y equals 6 and here's y equals 2. They're just horizontal lines. And then we have x equals 6. So 1, 2, 3, 4, 5, 6. And then we just have to put this other graph on there and figure out where it goes. So the formula is xy equals 6. And I'm going to actually just guess, pick points there. If x is 1, then y must be 6, because 1 times 6 is 6. So when we're at 1, we're at 6. And if x is 2, then y must be 3, because 2 times 3 is 6. If x is 3, then y must be 2. Again, 3 times 2 is 6. So basically, this is what our graph looks like. I kind of missed my point there. But you have a graph like this. So if I'm bounded by all of those things, so I'm bounded by y equals 6, y equals 2, x equals 6, and this line, now I can see the region. So the region that I have is right here. This is the part that I am revolving. Okay, so here is my region. So, first question says, let's revolve this around the line x equals 6. Then we're going to revolve it around y equals 6. So real quick, I'm just going to, whoa, not like that. I'm going to save this picture because then we're going to use it again. So let me go ahead and save this picture and copy it, because I'm going to need it again in a minute. So I'll move it out of the way here. Then I don't have to redraw it. Oh. Okay, so let's go back up. All right, so here's my graph, and I'm going to revolve it around x equals 6, which is this line right here. So if I'm going to draw my rectangle is going to have to be perpendicular to that line. That's what the disk method does, perpendicular. So here is a representative rectangle for revolving around the line x equals 6, which is right here. Okay, so the difference is when I revolve and get my cylinders, they're going around this way. Okay, so when I get a cylinder here, they've come around this side, okay, is where my cylinders are going to go. And that's a really bad drawing. No, let me take that last part off. But they're going to revolve around that side, okay? So it's going to look a lot different when we see this picture here. So if we were to continue on and kind of look at our cylinders, they're going to go around that direction, okay? So I'm going to actually take that off because that's confusing, but they're going a different direction. We have to think about that. But the process is exactly the same. The formula is always that volume of one of those cylinders is going to be pi r squared times the height. So the only thing we have to do is figure out what those things are. Well, the height is always the direction we have here. And so the direction of our rectangle is dy. So this is all going to be in terms of dy. So our height is simply going to be dy. So all we have to do is figure out how do we write the radius. So let's look at this very carefully. We have an original x and y axis, and that's really important to remember, that everything's in terms of that. So what I'm wanting is, how far is it from here to here? I need on any rectangle that I could draw, what is that height? Well, if I measure from this point to the end here, that measurement is 6, because that's the line x equals 6. If I go from here to here, that's going to be, to get to the top of the rectangle, that's just the function value. So to get the height of the rectangle, you're going to take 6 and you're going to subtract the function value. So you're going to have 6 minus, well, my function right now says xy equals 6, but I need it to say x equals something, because everything I'm doing is in terms of y. So I solve it and I get x equals y over 6. So I simply put that here. So x equals y over 6. So my function is y over 6. So 6 is the distance from the y-axis to the top of the rectangle, and the function value gives me the bottom of the rectangle. So 6 minus the function gives me the radius. And then I need to square it, and that's my volume of my cylinder. So if I want to do the volume of the entire figure, so let me scoot this down a little bit, then I'm going to integrate, because that means I add up a whole bunch of those cylinders over and over and over again. So again, keep the pi out in front. And I'm integrating with respect to y. Well, it's pretty simple to see where y goes. It goes from 2 to 6, because I had lines there guarding that. So we go 2 to 6, and we have 6 minus y over 6 squared dy. And that is my volume. So we can go through the process and multiply all this out, or we can just, I'm going to put it in the calculator and get the answer. But you might want to practice. Oh, and I wrote y over 6 instead of 6 over y. I just realized that. Sorry. Go back and change that in your notes. That's 6 over y. And when I solved it, I wrote 6 over y, and then I wrote y over 6 over here. So this is what I meant to write right there. So 6 over y. But if you put that in your calculator, you can get the answer. It wouldn't hurt you to practice by multiplying all of that out and doing the integration. You're going to get a natural log in there and a power function, that kind of thing. So you can do that process if you want. The most important thing is the setup. This is what's absolutely vital to be able to do, because the rest of it has nothing to do with this chapter. It's previous knowledge or it's calculator work. Okay. So now let's do the same problem, only this time, so take my same original picture, only this time I'm going to revolve it around the line y equals 6. That's this line up here on top, so this is where I'm going to revolve, around this line. So my rectangle then would have to be perpendicular to the line y equals 6. So let's draw a rectangle there. So here's a rectangle that is perpendicular to the line y equals 6. Well, here's a problem. If I move that rectangle over, notice that here it's between the lines y equals 6 and y equals 2, but when I get over here, all of a sudden, wait a minute, now it's going from the line to the curve. So I'm actually going to have two rectangles. So there's one rectangle. I'm going to basically have to split this into two pieces. So right here where they intersect, I'm going to have to make two different integrals. So I have one rectangle on one side and a different rectangle on the other side. So you're going to end up doing two different integrals to answer this question. So let's go ahead and do the first integral, which will be pi times the integral. Let's go ahead and do the one that goes from 1 to 3. So I'm going to do this little region right here. There's my representative rectangle, and it goes from 1 to 3. So I integrate this from 1 to 3. And I need to get my radius. So now let's think about how that's going to work. It's just going to be like the last time. The distance to go from here to here, which gets me to the top of a rectangle, is 6. Because remember, this was the line y equals 6. To get to the bottom of the rectangle is going to be the function value. So you're going to end up again with 6 minus the function. Only this time I need it to say y equals. So it'll be y equals 6 over x. So here you're going to have pi integral 1 to 3 radius, which is 6 minus 6 over x squared dx. So you have pi r squared. So the radius again, look at the green lines there. It's 6 to the top of the rectangle. It's the function to the bottom of the rectangle. So the height of the rectangle is 6 minus 6 over x. And then it's pi r squared times the height, which is dx. Plus, I have to have another integral for the other piece. Well, this is a super easy one. It's still going to be pi r squared, but this time the radius is clearly, the height of that rectangle is always 4. And I'm integrating from 3 to 6, and I'm just going to get 4 dx. So that second integral is super easy. 4 squared, radius squared. So I'm going to end up with, you can do your first integral, and you're going to get some stuff. And then you can do your second integral. So you can go ahead and do the process. If you need help with that, just let me know, and I will go through that with you in class. And this is your approximate one. So what I would do is go ahead and do both of those integrals, add them up, and see if you get this answer to check that. But that's the only thing that's a little bit different, is we're not revolving around the x or y axis, so we have to just make that correction. And then next time we're going to learn a method where we could turn the rectangle the other direction, even if we're going around the line y equals 6. And you can think about that, realizing you would only need one integral then, and so we just have a different method. So that's the reason that we can learn another method. Sometimes that method might be easier. So be sure you look over these problems and actually finish through them to make sure you're understanding.